Okay, welcome back. So, in my last class, I was starting your double integrals over rectangular domains. So, basically, what we were talking about, we are talking about double integral of the function f of xy over the rectangle A, rectangle R, okay? And rectangle R was simply defined as the set of all the points belonging to R2, where x lies in some interval AB and y lies in some interval C, as is yes. Okay, and I also told you that this is kind of one of the simplest cases because the domain, this R, it is not necessarily a rectangle all the time, but we'll come to that later on. And then again, there are certain properties involved with a double integral over a rectangle R. So I will quickly, I'll tell you about that quickly. And because anyway, when I'm going to talk about, double integral over an arbitrary domain D, so the same is going to be, valid there. So it is something like, say, if f is a, yes.
Your dA is dx dy, right?
Yeah. This is yes. dA is dx dy. Okay, or dy dx. So I am going to talk about the significance of that dx dy or dy dx from a short while from now. Okay. So now, let's say if f is a continuous function over defined over the rectangle R, so then what happens? Like say, if I consider say two functions. If I consider say two functions, okay. So then what happens? This you already know. Two functions, say your f and z, which are continuous over the rectangular region R. So then R, this double integral of R, this fxy plus gxy dA. So this is simply R fxy dA plus R your gxy dA. Okay, and again, if C is a constant, if C is a constant, then again this happens. R, C fxy dA. So you can simply take this out. Of course, this is a real constant dA. And again, if the functions f and g are such that your f of xy is greater than equal to g of xy, and it is for all xy belonging to that rectangle R. So then this is going to happen. R, the double integral of this is going to be greater than this. I think you have already appreciated this from your knowledge from single variable calculus. Okay. So now let us move to an important concept, and it is called your iterated integrals. Iterated integrals. What is this? Okay, so as I was told, like say when I consider this double integral, so in fact this dA is nothing but dx dy or dy dx. Okay, so now see here we have simply used the symbol of double integral over the region R. So we haven't talked about the order in which we are going to take the limits of I mean, the upper limit and lower limit of x and y. So that is where the question of iterated integral will come. So what is this? So before going to iterated integrals, let us talk about your partial integration. Let us talk about partial integration. So now you know that this one, I mean here R, it is simply the rectangle where x goes from A to B and y goes from, I mean, C to D, and then dA. So dA could be dx dy or dy dx. So in which order we should take it? So now what is partial integration? So with the help of this concept, I'll be able to arrive at a conclusion there. So what is that? Say suppose I consider I mean this integral. I mean okay, y equal to c to d, y equal to c to d. I mean f of xy, say dy, f of xy dy. So now you know that f is a function of two variables x and y. F is a function of two variables x and y. But what we do, if we assume that x is constant, or if we fix x, and then I mean say suppose I have something like say x squared y, f of xy equal to x squared y. So if I assume that I mean x is constant, and if I integrate this function with respect to y, keeping x constant, so whatever value I am going to get, you know that that is going to be a function of x eventually, isn't it? Right? So
Yes.
that is called yes. So that is called partial integration. So for example, if I integrate this function, say with respect to y, if I integrate this function with respect to y, keeping x constant, so this is simply going to give me x squared y squared divided by 2. Now, if I consider limit here, like if I consider this integral to be a definite integral, so if I take it from CD, so this is going to be y equal to C to y equal to D, right? So eventually you will see that this is simply x squared by 2, your d squared minus c squared. So eventually what you get this as a function of x. So this is going to be a function of x. So now, what is the concept of iterated integral? So what we can do, if we are considering this integral over the rectangle R, so then this what I can do, I can think it like x going from A to B, and then y going from C to D, f of xy, your dy dx. I can write it like this, and then you can see that your x equal to A to B. Now you have already seen that the expression within the bracket, it is simply some function of x, and this can be easily integrated, right? And eventually this is going to give you a number. And which is nothing but the value of this definite integral. Okay. So now, why it is called iterated integral? Because here we have kept x fixed and then integrated partially with respect to y. Now the same thing can be done by keeping y fixed and integrate the integrand partially with respect to x. Okay. So and there is a theorem called Fubini's theorem. Which tells you that eventually this integral I can write it as I mean y equal to c to d, and then x equal to a to b. Firstly, I can integrate this with respect to x. So again, this is going to give me some function of y, right? And then I can eventually integrate with respect to y, and I mean, eventually I'm going to get the definite integral. Okay, and the Fubini's theorem tells you that because say here the what order of integration we can exchange. Okay, so these kind of integrals are called iterated integrals. Okay, so and there is a theorem, and according to Fubini's theorem, these two are equal. Okay, these two are equal. Okay.
Sir, are there any conditions on fxy for them to be equal?
Fxy to be equal. No, condition means I mean, see here f has to be continuous there. That's it.
Yeah.
F has to be continuous. That's it. Okay. So what I'll do, I'll just quickly show you the slides. I'll just quickly show you the slides, and after that I'll move back to this. Yeah. So here, yes. So this is the Fubini's theorem. So if f is continuous on the rectangle R given by this, so then the integral of f over the rectangle R is simply what you can do. You can simply write either like this or either like this. Okay. And more generally, this is true if we assume that f is bounded on R. And again, this is interesting. See, even if f has finite number of discontinuities, over some smooth curves belonging to that domain of the function. Okay, and if this iterated integrals exist, they have to exist first. So then both of them are equal. Now here you can see the illustration of Fubini's theorem. So what it means, like say, when I keep x fixed, say suppose I'm giving x fixed. So then integrating with respect to y, it is going to give me a function of x only. And that function of x only, you can consider it to be the area of that region, which is nothing but a slice you have taken exactly at the location x. Okay, fine. And then yesterday we talked about volume integral. So volume integral, what you can do, you can simply consider a band, right? And then you can take sum of all those slices and you find out a volume. So you can think it to be like that. So similarly, if you firstly integrate with respect to y, integrate with respect to x, keeping y constant, so then it is going to give you a slice like this. Okay, so these weight portion, it is nothing but it is going to represent some area as a function of y. Okay, fine. So this is about iterated integral. So let us try to work out one example. Say suppose dA and R is given by this 0 to 0.5. So now you may be asking me, which integration we should take first? Integration with respect to x or integration with respect to y? See, what you have to do, both ways it is going to work. By Fubini's theorem, it is definitely going to work both ways. But you have to first see, which strategy is going to give you the, smoothest procedure. Okay. For example, here, what I'm going to do, see, this is, so, sine xy. So if I integrate with respect to, say, if I integrate with respect to x, say, with respect to x, right? So then I'm going to get a function of y. Is it okay? Fine?
Yes.
But if I integrate with respect to y, so then it is going to be difficult because I have another function of y here. Isn't it? So that is why what I'm going to do, rather I'm going to integrate this with respect to x. So y sine xy, since I'm integrating with respect to x, so x equal to 0 to 2, so it is dx, okay, and then y equal to 0 to pi, so this is equal to this, okay. So now since you're I mean I am going to integrate this partially with respect to x, my y is constant, and from here what I'm going to get, your minus cos xy divided by y, isn't it? Fine.
Yes.
So this is your then your x is going to go from 0 to 2 dy. So, and it is good that my y gets eliminated here. So now again, this is going to be what? Y equal to 0 to 2, this minus, so your
So 0 to pi.
0 to pi, sorry, 0 to pi. Thank you. So it is going to be cos your 2y and again cos 0, right? Cos 0. So yeah. So it is dy. So you can easily integrate it, and whatever value you get, I mean that is going to be your final answer. Okay. So do the next step yourself. Okay, so I'm just showing you an example. So now the next thing that we are going to do, it is very important, very important. So this is what I have been talking about. What is the next thing we are going to deal with? So it is double integrals over your general reasons. Double integral over general reasons. Okay. So as I have told you, that I mean the domain of definition of a function is not necessarily going to be a rectangle in the two-dimensional plan. Okay. So it can be any arbitrary set domain. Say suppose I am considering this to be the domain of a function, say continuous function f of xy. Okay, so then what we are going to do? The first thing is that I'm going to assume that this region is bounded. Okay, so that means we should be able to enclose it inside a rectangular. Yeah, no, not this, because this is going to be difficult here. Although, I mean, generally in 2D, what they do, if it is bounded, they assume that, I mean, they can enclose the region within inside a, I mean, a finite disk. Okay, but here, instead of disk, what we do? We are going to take a rectangular region, so that it is easier for us to integrate. So then, my next scenario, what I am going to do, say, suppose this was my this was my this. What I'm going to do, I'm going to enclose it. I'm going to enclose it inside. I'm going to enclose it inside a rectangle. I'm going to enclose it inside a rectangle. Say this. Okay, fine. Now, again, remember that the rectangle doesn't have to be such that it touches the lower and upper boundary and left and right boundary. It is not like that. It can be any finite rectangle. Okay, fine. So now what I'm going to do, I'm going to define a new function. See this original function. See, my aim was to find out integration of f of xy, integration of f of xy over division t. Okay, but now what I have done, I have generated a new domain. I have created a new domain, and it is basically I have created a rectangle, and inside that rectangle, my original domain is enclosed. Okay, so what I am going to do, I am going to define a new function. This is equal to f of xy if xy is in D's. Okay, and this is equal to 0 if xy belongs to, say, R, but not in D. Okay, I'm going to define it like this. So this is my rectangle R. This is my rectangle R. Okay, and this is my D. Okay, fine. So now this brings me an interesting situation. See, what is happening? Suppose this is my D. This is x, y, j. So then the graph of this function, it is going to be, say, something like this. Graph of this function is going to be something like this. Okay, so this is going to be graph of f of xy. For the time being, it is clear, right? Okay, so now let us see what graph of capital F of xy looks like. Okay, so again, okay, so this is my D. This is my D. This is R. This is R. Okay, so now, if you look at this definition, what it tells you that capital F of xy, it is exactly equal to small f of xy if it belongs to D. Otherwise, it is equal to 0 if it is inside R but not in D. So that means these portions are the graph of capital F of xy. Isn't it? Is it clear?
Yes.
Fine. So now this will give us a way. This will give us a way of your defining the definite integral or this double integral over a general region. Okay. So now and show you. And you would have probably imagined, I mean, what it is going to be, right? See, this is what I have told you. This is what I have told you. This is my original domain D, but now I have enclosed the domain D inside a rectangle R. Okay, and I have defined a new function capital F of xy as this. Okay, so then if capital F is integrable over R, then we define the double integral of small f over D, okay, which is nothing but this. It is defined as the integration of capital F over the rectangle R. Okay, so now that is very, isn't it? Because let me tell you what is happening here. Okay, capital F of x, y. So dA over this rectangle R. So this is equal to what? Capital F of xy dA in D, isn't it? And it is in complement of D. Is it okay? Fine?
Yes, sir.
Isn't it? Because R is the union of D and D complement, isn't it? So now over the region D, I have defined capital F as this, and in D complement, capital F is defined as 0. Fine. So this is going to give you 0. Fine. So that is why if I define this to be simply this, right, my justification is valid. Clear? Okay. So this brings me to a very important concept. I mean, so now let me tell you that whenever you want to perform double integral over a general region, the first task is about defining this general region D and enclosing it inside a rectangular domain. Okay, fine. So now let us see how we can do that. So you will see that, I mean, if or not if, you will see that we are going to do it through two approaches. We are going to define, I mean, this type of general regions D as of type 1 and type 2. And then I'll show you that any region you will be able to express as the union of type 1 or type 2 regions or both. That is what it is. Okay, and from there we can easily do the integration. So let us start. Okay, so type 1 region. So a region D is said to be of type 1 if it lies between two continuous curves defined as a function of x. So basically, if D contains points like this, that your x lies between A to B and y lies between this. Y lies between this. Then we say that this is a type 1 region. So it is something like this. Okay, why it should be symmetric? Goodness. I don't know why always I go for. Okay, so this is G2x, this is G1x, this is A, this is B, okay, and this shaded portion, it is the domain D. It is the domain D. Is it okay? So this kind of domain is called type 1 region. Okay, and I'm going to show you pictures of more, type 1 regions. Now, here, one thing I want to tell you is that, see, now, what is going to happen? Now, if I want to convert, like, say, this into something like this, if I want to convert this integral into this, where D is a type 1 region. So then what is going to happen? See, you can easily get some, rectangles like this, isn't it? Right? You can easily get something like this. Okay. So then what is going to happen? What is going to happen when your y is going to be lying between the graphs g1x and g2x? Then definitely your capital f of xy is going to be equal to small f of xy. But when your y is going to be less than equal to your g1x, okay, and y is going to be greater than equal to g2x, then what is going to happen? Your capital F of xy, that is going to be defined as 0, isn't it? So we will be able to perform the integration very easily. Is it okay? Fine. So that is what we are going to do. And another important thing I forgot to mention it. I'm going to show it to you. See, this is, so this is how we define it. So here again, I would like to tell you one thing. If I define my capital F to be the way it is described in the figure, like if your xy lies inside B, right? Then capital F of xy is small f xy, and if it is outside D but inside this rectangle, then the value of capital F is 0, like the way you are seeing here. So that means at the boundary of D, the function capital F, it is going to have discontinuity, isn't it? Is it okay?
Yes, sir.
Fine. But that is not going to create any problem if the boundary curve of D, it is well defined. Okay, fine. So that is one thing I would like to mention, and this I have already commented. And these are the type 1 regions. So these are the type 1 regions, as I have told you that a region D is said to be of type 1 if it lies between graphs of two continuous functions of x, that is D, and that is what I have been emphasizing on. See, whenever you want to perform double integration, it all boils down to defining that domain D accurately. Okay, see here I have got all this stuff. Here I have got all this. Okay, these are type 1 region. So similarly, a type 2 region is going to be when the region lies between two curves, described as a function of y. So this I have already explained how how the capital F is going to be defined for a type 1 region. So now, if that is so, how you define the definite integral? So if F is continuous of the type 1 region D such that this is the region I have already explained. So then the double integration is simply what you do. Firstly, you perform integration with respect to y, okay, between those two curves, and once you evaluate this, so this is going to give you a function of x, and then what you do, you integrate that function of x eventually, okay, between the limits a and b. So similarly, we can consider regions of type 2, which can be expressed as this D. You can see that y lies between C and D, and x lies between two graphs of functions defined in terms of the single variable y. So it is going to be something like this. And remember, sometimes what happens, you may be able to express a domain as type 1, both as type 1 and type 2. So in those cases, you have to choose which approach is going to give you the smoother procedure. Okay, so this is the way. I'm going to show you one example later on. So where a particular domain can be expressed as both type 1 and type 2. Okay, fine. So, and again, if it is a type 2 region, so then the definite integral. So what you do, you perform integration with respect to x first, and after that, because we have always defined iterated integrals, right? So then we perform integration with respect to y. So this is the way we are going to do. So let us try this one. Evaluate your this one d x plus dy dA, where d is the region bounded by the parabolas y equal to 2x squared and y equal to 1 plus x squared. So just let me take off the dust. Okay, so okay, as I have been emphasizing, the first thing is that you have to find out the domain D. Find out the domain D first. Okay, say obviously, if you want to find out the points of intersection of these two curves, so then what you are going to get, your 2x squared equal to 1 plus x squared, right? So this is going to give you x to be equal to eventually plus minus 1, right? So when x equal to 1, y equal to 2. When x equal to minus 1, y equal to 2. So just a minute. 1, 1, minus 1, 2, minus 2. So this is 1. just going to be flatter or steeper. Y is going to be equal to 2. So y ones. So okay, and okay, so it is going to be something like this. You will see a better version in the iterated. Okay, so basically this is y equal to 2x squared, and then this one is y equal to 1 plus x squared. Okay, this is 1, this is 2. So the points of intersections are 1, 2, and then your minus 1, 2. Okay, and this is my domain. This is my domain. This is my D. This is my domain D. Okay, so now you can see that D is D a type 1 reason or type 2 reason? Yes? You look at the graphs. Here, obviously, the graphs are given in terms of as a function of x, isn't it?
X.
So,
Yeah.
what I am going to do, I am going to use this as a x goes from minus 1 to 1, right? It will be something like this. Minus 1 to 1, and y goes from where to where?
0 to 2.
No. Y you have to express as a function of x. The y lies
Okay.
between these two graphs.
2x
Graphs
square.
are- Yes, 2x squared and 1 plus x squared.
1 plus x square.
Always remember. Here I have seen the students. I mean, they do a lot of confusion. So what is that? Whenever you consider, I mean, this graph as a function of x, you have to consider bottom and top. So the bottom is here 2x squared, the top is 1 plus x squared. Okay, and when you consider these graphs as a function of y, then you have to consider left and right. So if that is the strategy you adopt, so there is not going to be any confusion at all. Okay, fine. So see, we have completely defined our domain, right? So now it all boils down to, so that is why your x plus 2y dA, what I'm going to do, I'm going to write it as x equal to minus 1 to 1. Then y goes from 2x squared to 1 plus x squared. And obviously, my first integration is going to be with respect to y. Okay? And then, so now I can simply write it like this. So this is going to be what? Xy plus y squared, and this is 2x squared 1 plus x squared dx. So this is going to be minus 1 to 1. So it is going to be x into 1 plus x squared minus 2x squared. Then you are going to get 1 plus x squared whole square minus 4x to the power 4, right? Then and obvious yeah, then dx. Okay, so then you simply simplify and integrate it. The answer is giving you the slides. Okay, fine. I don't want to perform the integration further because this is very mechanical. And remember, it is all about finding this domain D. It is all about finding this domain D. Okay, so now let me come to a very interesting example which I had shown you when I started multiple integrals. So at that time, that problem may have sounded pretty complicated to you. So this let me just show you the domain. So this is what it is. Okay. So the answer is 32 by 50. Please try to work it at home. Okay. So now this is the problem. This is the problem. So find the volume of the socket that lies under the parabola j equal to x squared plus y squared above the region and above the region D in the xy plane bounded by the line y equal to 2x and the parabola y equal to x squared. So basically what you have to do, so j equal to x squared plus y squared, that is the function which we are going to integrate, because you know that if you want to find out the volume, lying below the graph of a function, and that function it has to lie above xy plane. So obviously the way the function is given here, x squared plus y squared, that is always non-negative, isn't it? So that is why we can simply consider the integral of this function over the region D as the required volume, right? So basically what you need to find the region D, and you have seen that the region D is nothing but it is the region bounded by the line y equal to 2x and the parabola y equal to x squared. Okay. So what we have to do here, y equal to 2x of parabola. So basically we have to evaluate this integral. Okay, and now and again D is the region bounded by the straight line y equal to 2x and the parabola y equal to x squared. Okay, so now what you have to do always, you find out the domain D first. Okay, so one, so this is 2, so this is the line y equal to 2x, and your this is the parabola. This is the parabola. This is your y equal to x squared. So if we want to find out the points of intersection, so what is going to happen here? So if you equate x squared equal to 2x, you are going to get x equal to your 0 and 2, isn't it? So one is going to be what? One is going to be
0, 0.
One is going to be 0, 0, and this is going to be 2, 4, right? This is going to be 2, 4. So now look, here is an interesting situation. And I'm not going to walk this problem out because you have seen that it is all about finding out the domain D. Okay, fine. See, domain D here, if I consider it to be a type 1 region. So then you will see that this is xy, and x obviously for this region 0 to 2, 0 to 2, and y bottom and top. What is the bottom one?
X square is the bottom.
Which one?
X square.
X squared. Yes. And the top is simply
2x.
2x. And again, interestingly, for the same problem, here I can consider it to be a type 2 result as well. Now here, y goes from 0 to 4. 0 to 4. Okay. And then x, again, here what you have to consider? Left and right.
Right. Yeah.
What is left here?
X equal to y by 2.
Yes, x equal to y by 2, and right x
Root over
is
y.
square root y. Yes. So after that, I mean, like the remaining part is straightforward, isn't it? Do I have to walk it out? I think you can easily do it, right?
Yeah.
Fine.
Yes.
It is all about simply, I mean, writing it down. And you please check at home. That both the approaches should result in the same way.
Same answer.
Okay. Yeah. So as I told you that this problem looks very complicated, but it is not. See, this is what it is. This is the surface z equal to x squared plus y squared, and this is y equal to 2x, and this is y equal to x squared. So eventually, this is the situation. Okay, I could consider this direction, or I could have taken a vector like along, I mean, horizontal vector. Okay, so D as a type 1 reason, and if D as a type 2 reason, it is actually going to be something like this, right? I think now you have enough understanding of this, how to work out a double integral. So basically, what you have to do, you have to simply concentrate on the domain D and how to express it as a type 1 reason or type 2 reason. Okay, fine. So now, what I am going to do, and there are further examples. I mean, the figures are already given. You please work it out at home, and of course, I mean, you are going to have enough problems in your tutorial sheets. So while working them out, also you have better understanding of whatever you have done. So these are the properties of double integrals. In fact, which we have already done, right, for rectangular domains, and these are for general regions. Right? These are general regions. So you can see that the same thing that I have done earlier. So instead of R, that rectangle, it is written as D. Okay, fine. So now let us come to a very important application of this one. Double integrals over type 1 and type 2 results. See, I have already told you that it is not necessary that the reason that is being given to you, it is going to be beautifully shaped so that you can convert easily into a type 1 or type 2 reason. It is not necessarily so. Sometimes what may happen that you have an arbitrarily shaped domain which is not directly fall into the category of type 1 or type 2. But if you examine more closely, then you will see that they can be expressed as a union of type 1 or type 2 reason. So that is where we are coming to. So this property of definite integral, like say the next property of double integral, is similar to the property of single integrals given by this equation. Okay, so if C is an intermediate point lying in the interval AB, so then you know that this definite integral for a function of one variable. So simply integral of f between a and b is simply integral of f between a and c and b, right? So likewise, if D is the union of two non-overlapping regions, D1 and D2. See here, they have written that D1 and D2 don't overlap except perhaps on their respective boundaries. Okay, fine. So then, in fact, we have already applied it, right? We have already applied it, isn't it? While doing the capital F of XY, that stuff, isn't it? Fine. So this is what happens. This is what happens. Okay. So then this is going to help you in decomposing a domain D, which is not explicitly a type 1 or type 2, as a union of type 1 and type 2 regions. Okay, so this property we are going to use there. So let us take one example. Okay, see, it is something like this. Say, for example, here, I mean, it doesn't look like a type 1 or type 2 region, right? But by simple introduction of a vertical line here, you can see that we can convert it into D union of a type 1 and type 2. For example, here the region D1, you can see that is bounded by these two curves, this one and this one, right? And again D2, it is bounded by this curve, this straight vertical line, right? And this curve. Is it okay? So here, this is a typical example where D1 is of type 1 and D2 is of type 2. Okay, so we'll work out an example, so then it is going to be clear. So, for example, let us consider this one. Let us consider this one. So, just let me quickly draw it, and after that, I will come back to blackboard. Y equal to x plus 1 squared, and this is like this. So this is this is 1, this is 0, 1, that's it. Okay. So y dp. Okay, fine. So now this is my domain. This is my domain. Okay. Am I still on or not? No? Yeah, I guess I'm still on. Okay. See, now obviously the whole domain D, it is not of, I mean, type 1 or type 2 type. Okay. But what I can do, I can convert it into 3 domains, D1, say D2, and D3. D3. So now let us concentrate on D1. So D1 obviously it lies between what? -1 to 0 along x-axis, okay? And this bottom curve, it is simply what? Y equal to 0, and the top curve is y equal to x plus 1 squared. So here D1, this is simply going to be your x lying between -1, 0 and y lying between 0, x plus 1 squared. Okay. Now let us concentrate on D2. Let us concentrate on D2. So are you going to express is a type 1 or type 2?
2.
2. So for that, y goes from obviously your 0 to 1. Yeah, and x goes from your 0 to
y minus y.
y2. Okay. And again D3 again, it is again type 2, right? It is again type 2 because I have left and right. left and right. Okay, and here, so this is here, y again lies between -1 and 0, right? And x lies between, this is x equal to, this line is x equal to -1, isn't it? X lies between -1 and obviously this curve is y minus
Y cube.
y cube. So I'm done, right? What you have to do? You simply make use of that iterated integrate concept for type 1 and type 2 regions. So what you do? Simply so this is going to be d1 y plus d2 y plus d3 y, and then because you have a description of all these domains, you can easily integrate it. Okay, so I think I'll just show you a couple of slides and then I will stop here. Yeah, so this is obvious. This is obvious. The next property of integral says that if we integrate the constant function f of xy equal to 1 over the region D, we get the area of D. This is obvious. Okay. So the proof is simply like this. Proof is simply like this. Okay. And again, this is also, you have done it in single variable calculus as well. So if small m lies with, if f lies with the small m and capital M for all xy belonging to a domain D, so then small m into area of D is less than equal to d double integral of f over D is less than equal to capital M into KD. Okay. And this next slide, it is going to be important. Suppose I am considering a region. I am considering a region, and it is not necessarily a two-dimensional region. I am talking about a three-dimensional region, and it is bounded by two surfaces given by z equal to z1 xy and z equal to z2 xy. And z2 is greater than equal to z1 for all xy lying in that region. Okay, so this is what it is. Suppose now that the solid region T lies above the plane region R. This is the plane region R. This is on a rectangle they are doing it, as before. But between the surfaces z equal to z1 xy and z2 xy. Whereas I have told you z2 is greater than equal to z1, and for all xy lying in this rectangle R. Okay, so then what we get? We get the volume V of this region T simply by subtracting the volume between z equal to z1 xy from the volume below z equal to z2 xy. So that is why volume simply becomes this. Okay, so and again, since I can easily, extend it to a general region. So now, if you have to find out, if suppose you are given an exercise where you have to find out the volume V of the solid T bounded by the planes z equal to 6. This is z equal to 6 and z equal to 2y. So this is z equal to 2y. Okay. And by the parabolic cylinders y equal to x squared and y equal to 2x squared. So this is the general region over which you have to perform this integration. So what simply you have to do, you have to simply use 5 in order to find out this volume. You please work this out at home. Okay. So I think with that note, I am going to finish today's class. So I will then see you in my next